Our next session is going to be on pneumatic robots.
Check.
It is going to be presented
Pointer.
by Mr. Ashwin Naidu. He is the technical director at Hydax Private Limited, graduate batch of 1997 in physics, math, and electronics from Bangalore University. Thereafter, he joined his family business, Elchem Technics Private Limited, and learned the nitty-gritties of the manufacturing industry. To hone his entrepreneurial skills, he acquired an MBA from Indiana University, Pennsylvania in 2007. Throughout his career, he has experimented with various applications of primary ECM technology, robotics, and energy systems, and remains a learner and an innovator at heart. His multifaceted personality involves teaching special needs children and practicing martial arts as a life skill. Ashwin is the national Muay Thai belt holder for 2023 and 24. After reviving Commodus 1972 Royal Enfield bullet bike last year, this year he is evolving in making a non-masonry part of the house from scratch. So let's give a round of applause for Mr. Ashwin.
Thank you. Actually, we both are involved in the house. And yeah, so I'll probably run some introduction on Mithali. Well, Mithali has got various experiences, and one of it is she started her career from the construction side, and now she's come on to the hydraulic side. You have to just speak very briefly. But nevertheless, in between, her journey has been pretty interesting. And yeah, one of her passions are fabric sciences. So I think we'll go over to the presentation. Yeah, so we're talking of a pneumatic robot with cylinder positioning. And it all started off when, Mithali asked me for some water. And then I said, don't worry, I'll make a robot for it. That was many, many years ago. So, yeah. As we all know about soft robotics, primarily soft robotics has always been using pneumatics, and it's got various explanations. In all of this, one thing which probably some of you might find this very interesting is this little bit of a research, and it's also turned into almost a product. I am not following it very much. Here, this bright Korean scientist, what he did was he bought about a low inertia arm and bought about a lot of joint stiffness. Now that was a bit of a motivating point for me, for us, to think about how we can bring about joint stiffness or rigidity, at the same time bring about softness.
Right, so we were looking at various methods of incorporating what we presented last year, which was pneumatic movement controlled hydraulically. And we took off from there. The idea was to make an application of it. So last year was plain theory, and this year we decided to bring the actual mechanism in place. It's been a year since we were working, so there were various other kinds that we explored. We explored the spine-like movement. There were the pneumatic joints, several joints pulled together. So we did try out several of these over a period of time, and then came to a combination of various joints which we put together to bring about the end robot.
So the concept here is very simple. We have two cylinders. One is pneumatically powered. One is just plain hydraulic oil, which is flowing in and out like a closed circuit. You shut off the cylinder, it positions itself. Both the cylinders are connected in tangent. Yeah, gamification of operations. I think Mithali is a better person here.
Right. So this is one of the ideas that we've been exploring from a long time. Since COVID, this idea actually started during that time when we experimented with the pulley kind, it didn't work. And I think the starting point was automating the operations. But then the traditional means turned out to be very expensive. So we wanted to replicate the human, right, with the inaccuracy that a human hand could have, right? So the whole robo has been designed where it is semi-autonomous. The gross movements are pre-programmed. So pretty much if you're trying to take it from one position to another, that part of it is programmed. But the fine-tuning it fit, and more than anything, it is just the monitoring. So it's like a master-slave arrangement. The monitoring of it can be done remotely by a person. So it's almost like gaming. I must say we are also working on the software part of it, and I wish today we had the mobile to give it to any of you all to operate the robo, which is here right now, and we've brought a working model for that purpose.
Yeah, so the algorithm that was proposed, as you can see here, so we look at the gross motor skills, and then it goes up, and it positions itself. And if the position is not okay, then a person sitting remote resets the position, and the operation is done. Yeah, probably most of you may be asking, why is that we have to do if we can use a robo for complete automation? But again, it's the cost, and we're trying to bring automation to the MSME sector.
The idea right from the beginning was that it has to be a remote operation. It simply did not make sense to have another person on the shop floor and then call it autonomous. Then the whole concept would not work. So there is a software which we have developed in-house where the robo can be operated remotely from anyone through our server and from any part of the world, and it can be operated through the software that we have written.
So we are looking at how we can bring the gaming community, bring about a gainful employment, and not pay FPTS, PF, because probably they're just gaming and enjoying. And yeah, most of the industries could do work with that if it goes by all the laws. This was the proposed Rosa.
These were the various joints that we looked at, the combination of joints. So joint A is a rotary joint. Yep. Then we have joint B, B and C, which are the linear joints. And then, joint D is the linear joint, right? And so these together, so these are the various movements that are shown, okay? They are not multiple arms. It's one single arm, but which is showing all the different possible movements.
Why we chose this design is primarily because we wanted to experiment, play around with various joints, a rotary, an elbow, a linear, and let's see what happens. This was the range of motion. You can see here it's all in millimeters, and so you can position it like an arc anywhere around and extend it straight in. Of course, they don't have an end effector. The end effector will require another 2 axes. We have not got there yet. And the rotation is about 120 degrees. This is the rotary joint.
Yep. The rotary joint is right at the base, which gives the all-round movement. Yeah.
And then you have your elbow joint, which is pretty much like any other JCB. Now, I must share something with you. I've always read about singularity, understood a lot about singularity, but for the first time in my life, I actually saw singularity, right? So singularity is when you have multi-levers where you need an infinite amount of force, and basically the levers are stuck, to put it in simple language. And we didn't get it right the first time. When we designed it, we didn't use a complex software to understand singularity, but we were just using simple solid edge or solid 3D CAM to understand motion, but that led to a lot of similarities. This is the linear slide.
Yeah, these are slide joints and thereon it can have your the end effectors from that point on, which we have left open for the moment because I mean, it's pretty much open for anyone to use for whatever application that they see fit, right? We have focused mainly on all the getting the joints in place, but not the end effectors, right?
So, yeah, we have the joint testing. So we have a live demo there as well as the video over here. So this is each joint where you can see here it stops at various positions. In the video it stops, but here right now, since the objective was not to talk about AI, the objective was to show multiple joints working pneumatically but yet able to position. You will not be able to see it stop midway perfectly because we have just made it go at random positions. And this is again a linear joint testing. We can keep running it. So we have a linear joint over here, you can see. So stop means it stops in between, go it goes in between. And over to the next slide. Now this is the elbow joint, and we have two elbow joints. So we were looking at how a robot can go this way as well as go this way. Then Singularity you know, made us go only so much and only so much. We are still going to work on it.
An honest confession, as much as we started work on this last year, like all college students, we decided to bring it up only the last minute. And we started work on it, and we had a different problem, and we had to rework the entire thing. And last night, yesterday evening was the first time it was all put together and it started working. So here it is, and yeah, there's lots more to be done in terms of especially the, right now it's a pre-programmed. Once we integrate the software into it, which the software part has been done, but we need to put it in place out here, it can actually be controlled by any of you all in the audience.
Yeah, it can be controlled by any of us all, and the most important sensor for the AI is the camera. The image, it works completely on image and not any other positioning system. So if it sees a human, it stops. If it sees certain colors, it goes. Certain colors, it stops. So we did not bring the software part because this is purely a hydraulic, you know, seminar. Yeah, the load, so in the previous paper we had tested the linear axis with the load, and it was designed for about 16 kgs and it works successfully. So you can refer to the previous paper. Alright, so I don't know, I have to ask Mithali if she still wants robo with water, to bring water.
Yeah, actually, it started with that last year where the whole robo, when we spoke about it, was every time we sat to eat a meal and there was suddenly somebody who wanted water, and I said, you like robotics so much, why don't you make a robo to fetch water? So he says, now do you still want water at the table?
Yeah. So this, I know most of you are surprised as to why we are using pneumatics and why not servo. So just a quick recap of my last year's paper was that the cost of a joint, a robotic joint, will be anywhere between $1.5 lakh to $2.5 lakh, depends on various other conditions. And also so basically you're looking at a very, very rigid robot, a huge amount of inertia being managed to a final endpoint, which is probably about a payload of 5 kgs. And if you want to reduce the inertia, and if you want to reduce the and yet have certain amount of joint stiffness, and yet make it economical, yet make it easily available with some things like pneumatics, then you need to have a very clever software for it, a very clever AI for it. And that's not a part of today's presentation. But over to all of you, please do feel free to shoot the idea down, because we will learn something from it.
And I think the one specifically, the point we want to mention about this is all of the software and development regarding this has been put up on GitHub, which we have been doing over the last few years. So for the community to add to comment on, it's all available there, including the latest version that we have. We haven't put it on the right.
Yeah.
So we have DRosa, our website,
DRosa.ai,
which is free of cost and for everyone to use for any of those apps which can be used for your end application.
various. So we have, it's an online, what to say, an AI which is growing, and you just log in using your Google account and you can play around with it. A lot of it, it's not a complex system, but if you want to control a few relays, you just enter the IP address and you can control a few relays if you want visual inspection. So there are various things that can happen in that. Somebody had a question there.
Yeah.
I don't have the mic. Could someone please?
Yeah, thank you for beautiful presentations. And this would be a unique development which we see with the pneumatics, where we can see a development of a robo with different coordinates, joints, and which can have a multiple different angles of the rotations. My question to you is, what about the repeatable accuracy of this system? Because today we are talking of games. This could be used for different various industries. And I believe all the people who are present here are from different industries, different business segments, which we are using for automobile, electronics, food and packaging, pharma, going ahead with the bionics, and semicon, with the which upcoming industry. So repeatable accuracy and the air consumption of this.
Yeah.
Because today we are talking in Europe and all, it has started that we have to reduce the pneumatics, where we are speaking of servos, which you speak about the lakhs and all, it will going to cost for the joints. How about the pneumatics and the safety of the pneumatics?
So speaking of the accuracy, we have achieved the linear accuracy by 0.5, 2.5. So once again, as I said, it's not just pneumatic air. Pneumatic air is just giving the power. The position is done hydraulically, meaning which it's not a separate hydraulic pump, but it just stops. Now this is purely a concept which we are experimenting on, and we are yet to see the final accuracy of it. And when we speak about a lights out factory, so you have a lights out factory which is this country, which can run completely on custom made, like the Chinese, for example, are working on custom made robots for custom made applications. And therefore they are being able to do lights out factory. And then whereas you have another spectrum of countries, like say maybe Japan, who make robots using robots. And there again it's lights out. Now we are somewhere floating somewhere in between this and this, you know. So we are just purely trying to experiment and see how good it can get. Now, since the repeatability is 0.5, so with all the access put together, probably it's a millimeter. But again, since we are talking of a low volume of production, and we are talking of a person sitting there and the software is guiding that person. So the person sits in front of a monitor, so he doesn't have to come to the factory. That can be anywhere in India, and then or anywhere in the world, and then he sees the position is not okay, set the position for this and then run it. So 3-minute cycle time, he gets about 20 seconds to reposition it. Again, the reposition is completely AI driven. So we have various APIs which are running, which are going to correct itself and do it. So this is purely the mechanical output for the AI.
I think the question is, moment we look at a robo, we are imagining the robo will do all of this. But here, this is not the case. It is an assistant, yeah? So it has its limitations, but then it is not meant to do the end job. So we have to take ourselves out of that mindset which says like, this will do everything for us. It is not our slave. In fact, it's the other way around. It's the master and the gamer is the slave who's actually trying to, position it in place. So the mechanism for getting the accuracy is not dependent on this object, but is dependent on the visual media, which is again controlled by the software, right? So it's a different loop. It's like this rather than this reaching out, okay? So I think we've just tried to realign the thought that Rosa will do the job. No, she will not. So.
I didn't know it was a she.
Just like that.
Okay, I think thank you for the information and all the best for the developments.
Thank you so much.
Right. Also, it was purely
Any-
for the purpose of R&D. There is no commercial gain or aspect that we even at this point in time even think will come out of it. But please feel free to share all your views, to debunk it, say everything that's wrong with it, few things that may be right with it also.
Yeah.
I think one thing.
Any other questions?
In
also,
one
please?
of the earlier slides, here, the chair is speaking.
Oh, okay.
Yeah. One of the earlier slide, you were showing the gross movement and the finer movement. I think that's a very good concept because the cost of gross movement obviously will be lower compared to bringing that accuracy in the final picking of the object or whatever it is. I think it's a very good concept. So I think it will bring down the cost of so-called robots.
Well, at least for us to get it at this level, it costed very little. We are a small-scale industry, a very poor industry, and so for us to talk of robotics is,
Again.
Any other questions?
Yeah.
Please.
So the current industrial robot, which is used to place the object on a machine and take it back, it costs somewhere around 35 lakhs. What is the target cost that you are aiming at?
We have never gone till there yet.
No, some aim, some target.
See, the current 6-axis robo, I have come across a person, an ex-IITN, who is running this industry, who is running an industry there. And he tried to bring it to 20 lakhs. And he was telling Ashwin, whatever we do, a 6-axis robot cannot be less than 20 for a payload of 5 kg. And then, so I suppose in this case, the mechanical system, as you see, is just like on JCB. Nothing phenomenally innovative or anything like that. But the cost could be probably less than 20. But of course, you have the software, the AI, which is again a community-based, and it should grow from there.
I find things are not smooth movement. So
so we are not running at the proper air capacity. Okay. So we have a compressor somewhere very far up there. So there's a lag, and it's a very small 50-liter capacitor. We are using 100 dia cylinders, 100 stroke. So, air is consumed.
Okay, thank you.
For a change, we will ask you a question. How much you are willing to pay?
Right. Thank you. That gives us the benchmark, right?
See, I definitely feel that any equipment which is designed should be used by an MSME, reasonable level of cost. And it should be used by most of the MSMEs. So I would target it somewhere around 5 to 6 lakhs.
Okay.
Right. Thank you.
Thank you, everybody.
I think,
and please do feel free to write to us. It's Ashwin at Hydax India, Mitali at Hydax India. Please write your comments. Thank you.
And thank you very much. On behalf of Fluid Power Society, a small memento.